right, so we are switching out from a Newtonian model where we look at forces alone, and we are switching into the work and energy model. So to figure out how to use this model, we are first going to need to define our terms. So the first kind of energy that we learned about in today's reading is kinetic energy. And just like the kinetic of kinetic friction, kinetic energy is energy you got because you're moving. So we'll use a big K to symbolize that. It is 1/2 the mass times the speed of an object squared. So clearly, if you've got any speed and you have mass, which of course means in physics that you're just an object, so you have speed and mass, then you've got kinetic energy. Work is a little bit trickier because it has an integral. So work is the path integral, meaning I go from point A to point B and I walk along some path. And as I walk along that path, I look at the dot product between the force acting on me and the tiny little bit of displacement along my path. So let's draw out a picture. I got A, I got B, I walk along a path from A to B. Right here on the path, there's my teeny tiny little displacement dr. And I look at the force that's acting on me, maybe right there, it's in that direction. And I do the dot product in between them. Maybe a little bit later, here's my little bit of path, but now maybe the force is off in a different direction. Maybe the force is like that there. So at this point in the path, I'll look at the dot product between the force and my little bit of displacement. And I do that at every single little point along my path, add up all of those dot products, and that's my path integral. Fortunately, there are a lot of times where we don't have to do this integral. We can look at a simplified version of that. So I'm going to erase out this so I have some room to work. All right, so my simpler case is if the force is constant. So the force isn't changing direction or size anywhere along this path. And let's make it even more simpler. And the path is a straight line. Then we can really simplify this. So first of all, if force is a constant, then constants, they can come out of integrals. So this will be force dotted with this path integral from A to B. But if it's a straight line, then if we integrate over this path between these two, it's just going to be the displacement or the change in position. We'll call that D. And let's go ahead and spell that right. Displacement, that's what D stands for. And that is just the length of the path from point A to point B. All right, so if we've got this simpler definition of work, well, what does that mean? I guess we take the force vector and we multiply it by the displacement vector with the dot product. Well, what does that mean? Let's review quick what the dot product is. I'm going to erase all of this and just leave out my simplest case. Okay, so I wrote up just the simple case. We're considering force is constant and the path is a straight line. It's got a length D. Then work is force dotted with the displacement D. All right, so what is the dot or the scalar product? You'll hear both of those terms, dot product and scalar product, pretty interchangeably, so just be on the lookout for either of them. All right, so the dot or the scalar product. So say we've got two vectors, we'll call them A and B, and they will have, make B just a little bit longer so it's not quite so cramped. B will be like that. And they've got this angle in between them. So those are my two vectors. If I want to know what is the dot product of A and B, well, there are two definitions I can use. One, I can multiply the magnitudes of those two vectors, the lengths of the vectors, and then multiply them by the cosine of the angle between them, or I can multiply each of their components together. So the x components of A and B together, and then add them to the y components. Oops, let's write it in the right order. Y components of A and B, and then finally the z components. All right, so what is the dot or scalar product doing? Well, to look at that, let's maybe group this a little bit differently. And I'm just going to scooch it out to give myself a little more room. So we have the magnitude of A, the magnitude of B, and the cosine of the angle between them. What if we group it like that? So what is the magnitude of B times the cosine of that angle? Well, if you're thinking in terms of vectors and components, that's the hypotenuse of the V vector. And the cosine, well, let's see, if we're thinking of this guy and we're dividing it up into components, draw in our little right triangle. There we go, there's the right triangle. The hypotenuse times the cosine, that's going to be the adjacent side. So that's this right here. That is B times the cosine of that angle. It is the component of B which is parallel to the A vector. And of course, now that we know that what we're doing is we're finding how much of B is parallel to A, it actually works the other way around. We could flip those two magnitudes and look at the piece of A which was parallel to B. Well, we also see that's happening here. We're taking the x components, they're parallel, or anti-parallel. In this case, it's the same thing. They're on the same axis, those x components. So are the y components and the z components. So what the dot or the scalar product is doing is it is looking at two vectors, grabbing their parallel pieces, parallel or anti-parallel, the pieces that are on the same axes, and it's multiplying those together. So for some reason, for work, we need to find what if the force is parallel or anti-parallel to the displacement of the object. That's the important bit when we look at the work done by this force. And there's one other thing that's going to be a little bit different here in the work and energy model than it was in the force. All right, so you got the dot and scalar product. These are the definitions mathematically. The important thing to take away here is this guy is finding the parallel and anti-parallel pieces of the vector. So for the simpler case where we've got force is constant and path is along a straight line, where work is just the force dotted with the displacement, let's draw out two different scenarios. The first one, we'll have a little object. It's moving this way, that's its displacement. And the force is in the opposite direction of the displacement. So the force is off this direction. Whereas over here, we have the same little object. It's got the same displacement, but now the force is going in the same direction as that displacement. So again, we remember this guy is going to be equal to the magnitude of the force times the magnitude of displacement times the cosine of that angle in between them. Here, the angle in between them is 0. So cosine of 0 is 1. So here, work is equal to the magnitude of the force times the displacement, and it's positive. Versus over here, well, there is 180 degrees between these two vectors. So the cosine of 180 degrees is -1. So in this case, the work is equal to negative times the force of the displacement. And again, just to write it out, it's negative here. And how we interpret this? Well, when we were doing forces and accelerations, the negative and positive were directions. You were going this way or you going that way, depending on which way we had defined as positive. The negative and positive signs told you which way you were going. Negative and positive is a little bit different in the work and energy model. We're using it to model something different. So in this case, where the force and the displacement are in the same direction, they're truly parallel here, and work is positive, what this is actually saying is there's positive work being done on this object, and that means there's energy being given to this object, because that's what work really is. Work is a way to keep track of how energy is flowing into and out of objects. So when you see a positive work, that means a force is giving energy to an object. It is pushing in the direction it's moving. So just from what we know from Newton's second law, this force would tend to accelerate or give more speed to this object, obviously giving it more kinetic energy. So that's what a positive work on an object means. A negative work, on the other hand, that means that this force is taking energy out of this object. So when a force does negative work on an object, it's removing energy from that object. And that sort of makes sense from what we know what's going on with the Newtonian model. If an object is moving that way, but there was a force on it this way, that's the only force, that's the net force, then that force is going to tend to make it slow down. The velocity is this way, but the force, and if it's the net force, the acceleration is in this direction, so the velocity is going to get smaller and smaller. And that will obviously reduce its kinetic energy. So here, a negative work means the object's losing energy to that force. So that's kind of what work is doing, and that's also why we needed the force and the displacement to be parallel, why we had to use the scalar product, because it's pulling out the parallel pieces. Because only forces that are in the same direction, if it's going from here to there, then it must mean its velocity is this way. Only forces, and thus accelerations, which are in the same direction as motion, are going to speed it up, give it more kinetic energy. Versus over here, where the velocity must be in that direction, forces and thus accelerations, which are anti-parallel to the velocity and thus slowing it down and thus reducing its speed and taking away kinetic energy, well, those works are negative, and that's because those forces are removing energy from these objects. So that's the gist of work and energy. We'll go into a little more into details later, but for now, get some practice calculating kinetic energies and the amount of work done on objects.